Hello, welcome to Get to Aerospace Lab. This is the second video on Propulsion previous year question solution series. In this video, we will solve the Propulsion question from 2008 paper. Let's take the first question. See, in this first question, it is given that in a scramjet engine, okay, the Mach number at the entry to the combustion chamber. Okay, first of all, we will see what is a scramjet engine. See, the scramjet engine stands for supersonic as supersonic C combustion ramjet engine. Okay, see, in a ramjet engine, even though the entry is supersonic, at the time of combustion the flow is subsonic, whereas in a scramjet engine the flow at the entry as well as throughout the engine is supersonic only. So C is our answer. Fine. The second question, it is asking, in a CD nozzle of a rocket motor, the wall heat flux is maximum. Okay, the first statement is at the exit of the divergent portion of CD nozzle. No. Then at the entry of the convergent portion, that is it is telling us about, if this is the motor and this is our nozzle, CD nozzle, this is our throat, at the entry of the it is asking about this point. Okay, so from here onwards, if you will see, the expansion starts. That is, expansion start means the temperature will keep on decreasing. Okay, as the flow progresses from this point at the entry of convergent portion to the exit of the divergent portion, the temperature will keep on decreasing because it's expansion. Okay, that means we are having the maximum temperature here. If the temperature is maximum here, then of course the heat flux will be maximum at this section only. So our answer is B. Fine. Third question, dB denotes the double base solid propellant. Okay, so dB is basically a solid propellant. Now LOX RP1 denotes the liquid oxygen and kerosene combination. Okay, LOX and LS2 denotes the liquid oxygen and liquid hydrogen combination. Then what we have to do? We have to arrange this in increasing specific impulse. Fine. You see, first of all, I will tell you, for a solid propellant, the value of ISP, the typical value of ISP will be between 285 to 295 seconds. For a cryo engine, the value of a specific hit will be close to 450 seconds. Then for a semi-cryo engine, the value of ISP will be something around 360 to 365 seconds. Now if you will see the propellant given to us, dB, whatever they have told, it's basically a solid propellant. This LOX and RP1, this is basically a semi-cryo engine. Then this liquid oxygen and liquid hydrogen is the fuel for a cryo engine. Now from our this ranges, we can tell for this we will be having something around 285 to 295 seconds ISP. For this we will be having something around 360 seconds, and for this it will be around 450 seconds. Now if you will arrange this will have the maximum. So this is the minimum. So if you see this option, A is satisfying our criteria. So A is the answer. Okay. Now please read about the semi-cryo engine. and cryo engine. What is the difference between these two engines? And you can put your answer inside the comment box. Okay, just comment your answer in our comment box. Next question is, a turbofan engine has a bypass ratio of 5. If you see, bypass ratio is what? It means the ratio of cold stream to the hot stream, that is equals to 5. The total mass flow rate, that means what? Cold flow and hot mass flow will be equals to 120 kg per second. The mass flow rate through bypass duct, that means what? For a turbofan engine, we know that there are two flow streams. One is the main stream, that is the hot stream, and one is the cold stream, right? So they're asking us to find out the through the bypass duct. This is the bypass duct, so we have to determine the mass flow rate of cold stream. Okay, from this if you see, this MC will be equals to 5 times of MH. So this will become 5 times of MH plus MH is equals to 120. So the value of MH will be equals to 20 kg per second. Now if MH is 20 kg per second, then what is the value of cold stream? This will be 100 kg per second. Fine, this was an easy question only. So this is B is our answer. Now the next question is the fifth question. A turbojet engine is operating with afterburner off. Okay, if afterburner is switched on, then we know in the last video also we have discussed that afterburner is what? Afterburner is used to increase thrust at the expense of fuel. Fine. So this criteria, if you will see which one is satisfying, thrust will increase, okay, but no, this is wrong. And thrust increases and SFT, no, I think D is the answer. Fine. Now the next question is from the compressor. The centrifugal compressor operate with tip blade speed of, that means U2 is given to you, that is 340 meter per second. Air leaves the impeller with the radial velocity. Radial velocity at the exit is given as 88 meter per second. The slip factor value is given as 0.85. Now we have to determine the relative velocity at the tip. That means we have determined W2. Fine. Now I will draw the velocity diagram for this situation. You see, the velocity diagram will be something like this. This is the radial velocity. Okay, this is the absolute velocity at the exit. This full is the U2. Now if you will see, this is mu is 0.85. That means this is only 15% of your U2. Okay, then this one we have to determine. Now if you see this triangle, then we know the value of VR2, you know the value of U2, then W2 will be equals to root under VR2 square plus 0.15 U2 square. Then this will be equals to 88 square plus 0.15 into 340 square. If you will compute this, you will get 101.71 meter per second. So the answer is A. Okay. Next question. You see in this question, an ideal ramjet engine is flying at Mach number of m. Okay. The exhaust static temperature at the TE is the temperature at the exit, and TA is the ambient temperature, static ambient temperature. R is the gas constant, specific heat is gamma. Then assuming the nozzle exit, this is very important, nozzle exhaust static pressure is equals to the ambient pressure. What is the meaning of this? That means no pressure thrust. Okay, only momentum thrust will be there. Then we have to neglect the mass of the fuel. The thrust per unit mass, you know how the thrust expression will look like now. The mass flow rate into velocity of exit minus mass flow rate into velocity at the entry. Okay, now we have to determine T by M. This will be equals to VE minus VA. Now if I take VA as common, then it will be VE minus VA minus 1. Now we know that for a ramjet engine, if you will see, Mach number at inlet will be equals to Mach number at the exit. Correct? That means velocity at, and that we say it is m. So this will be VE is equals to m of root under gamma r TE, and VA will be equals to m root under gamma r TA. If you will plug in this value here, this value will be m root under gamma r TA. If you will put these values here, you will get TE divided by TA root under minus 1. Okay, so if you will see, this is corresponding to our option C. Fine. Now next question. See, in this question, the degree of reaction is given. It's an axial flow turbine with the value of R given as 0.5. With the mean blade speed is also given. U is 180. The flow leaves the stator and enters the rotor at 60 degree. That means alpha 2 is equals to 60 degree. The axial velocity is given 150 meter per second, and it remains constant throughout the stage. The turbine power for per unit mass, if you will see our velocity diagram, it will be like this. Okay, this is our U, this is alpha 2, this is alpha 3. We know that work done is equals to CA U tan of alpha 2 plus tan of alpha 3. Now for the unit mass, right? Now we also know that reaction, degree of reaction is given as 1 minus CA by 2U tan of alpha 2 minus tan of alpha 3. Now this is 0.5 is equals to 1 minus, what is the value of CA? 150 divided by 2 into U is 180, this is meter per second, into 1060 minus 10 of alpha 3. If you will solve this, you will get the value of 10 alpha 3, which will be equals to 0.532. Now in this expression, we will put the corresponding values. 150 into U is 180. We know the value of 10 alpha to 1060 plus this is 0.532. This will come to be out 61129.4, which is equivalent to 61.13. So this T will be our answer, kilojoule. This will be in kilojoule per kg. Fine. Now we'll see the next question. Now in this question, see, the chamber stagnation temperature is given. Okay, the rocket, inside the rocket engine, let's say it's a solid propellant, the chamber is having TC total temperature. There is only convergent part. Fine. Then flow through the exit of the nozzle is choked. That means here you will have Mach 1. It is choked. assume that nozzle exhaust static pressure is equals to, that means PE is equals to PA, that is no pressure thrust. Gas constant is R, gamma is given. We have to determine the specific impulse. You see, what is a specific impulse? A specific impulse by thrust for unit weight, mass of propellant into G. So this you can write it as VE divided by mass of propellant by Z. Then this would be equals to VE by G. First of all, we'll determine the VE. How to determine the VE? See, VE for a choked flow will be given as gamma R TE. Okay. Now this TE, how to determine? See, we know the total temperature to a static temperature relation 1 plus gamma minus 1 by 2 into m square. Same you will apply in this case also. Tc is the total temperature, Te is the static temperature, will be equals to 1 plus gamma minus 1 by 2. Here Mach is 1, so into 1 square. This will come as gamma plus 1 by 2. So from here you will get Te is equals to 2 Tc by gamma plus 1. Okay. Now this Te will plug in here. So VE will be equals to gamma R TE is 2 R Tc divided by gamma plus 1. Okay, root under. So this is the exhaust velocity, but what we have to determine? We have to determine the ISP, specific impulse, which is what we have seen. This is equals to VE by G. So actually it should be 1 by G root under 2 gamma R Tc divided by gamma plus 1. But if you see, this is not there in our option. So I think there was some problem with this question, and the answer sheet is showing D as the answer. Okay. Now next question is, air enters the combustor of a gas turbine engine with total temperature of 500 Kelvin. So this is our combustion. Then it enters with 500 Kelvin and leaves it with 1800 Kelvin. Okay. Cp is also given 1.005 kilojoule per kg Kelvin. Heating value of the fuel is also given. Calorific value is given 44 megajoule per kg. Okay. Then if we will apply, we need to determine the fuel to air ratio. How to determine this? If you apply the energy balance in this system, then in that case whatever energy you will get from fuel, that is mf, mass of the fuel, into Cv, the calorific value of the fuel, that will increase the temperature of the gas. So that should be equals to mass of fuel plus mass of air into Cp, increasing its temperature of 1800 minus 500. So to take mf to this side, this implies 44 into 10 to the power 6 will be equals to 1 plus mass of air by mass of fuel into 10 to the power 3 into 1300. Okay, we need to determine mass of fuel by mass of air. If you will solve this, you will get mass of air by mass of fuel as 44 into 10 to the power 6 divided by 1.005 into 10 to the power 3 into 1300 minus 1. If you will solve this, you will get the value of mf by ma something close to 0.0306. If you will see, this value is close to the option C. So option C is our answer. This question, okay, in this question, the initial temperature sensitivity of burn rate of solid rocket motor propellant is positive. Okay, if the initial temperature is increased, first of all, there is a mathematical model for rate of burning, which is A into P naught to the power N, where R is our burn rate. Okay, A is a constant that depends on initial temperature of the propellant. P naught is total pressure inside combustion chamber. Okay, now in this question, what it is telling is that initial temperature increases. Okay, that means if you are telling us that temperature increasing, initial temperature increasing, that implies your value of A increase. The value of A you are increasing, then from this relation you can tell rate of burn increases. Okay, if rate of burn increases, that means what? Your burn time of burn will decrease because you have increased the rate of burning. Okay, so time of burn will decrease, time to burn the propellant will decrease. And if your rate is increasing, burning rate is increasing, that means what? Your propellant mass flow through the nozzle is also increasing, velocity is also increasing. So if your mass is increasing, velocity flow is also increasing, that means your thrust is also increasing. Thrust will also increase. It implies thrust increase, burn time decrease. Which one is our option? Our option is option A. Fine. Next question. In this question, an aircraft is cruising at Mach 0.8, where the ambient static pressure is given 95 kPa. The total pressure is also given 140 kPa. There is no change in a specific heat, that means gamma is 1.4, it is also given. We have to determine the adiabatic efficiency, okay, of the intake. Fine. You see, the process is adiabatic, that means you can represent it, this intake process, as P naught by Pa plus gamma minus 1 by 2 into Mach square into efficiency to the power gamma by gamma minus 1. Now it is a very easy problem. Now you just enter the value of Pa, P naught, okay, the value of Mach number, then this will be equals to 140 by 95 is equals to 1 plus gamma minus 1 is 0.2 into 0.8 square into efficiency. This will be equals to 1.4 divided by 0.4. If you solve this equation, you will get the value of efficiency as 0.915. This is option B. Okay. Next question. In this question, ratio of oxidizer to fuel is given. Ratio mass rate flow of oxidizer to fuel is 5, and it produces a thrust of 10 to the power 6 Newton. The initial mass is given as 100,000 kg. Then the final mass is also given, that is 10,000 kg. The characteristics velocity, which is given as P naught A star divided by mass flow rate of propellant, okay, which is 2386, and CF, which is the ratio of thrust to P naught into A bar, is given as 1.4. okay. Now if you see, this propellant means what? The propellant is the combination of fuel plus oxidizer. Okay. Now in this question, the first question, the mass flow rate of fuel is asked. How to determine this? We'll see. You see this two term, then if you will multiply these two term, you will get C star into Cf will be equals to P naught A star divided by mass flow rate of propellant into thrust P naught into A star. This will get cancelled. So this equation will become 1.4 into 2386, that will be equals to thrust, which is 10 to the power 6, mass flow rate of propellant. If you will solve this, you will get the mass flow rate of propellant, which will come as 299.36 meter per second. Sorry. The mass flow rate of propellant you will get. The mass flow rate of propellant is 299.36 kg per second. This is for propellant. It is a combination of mass flow rate of fuel plus mass flow rate of oxidizer. Okay. Now we will use this equation. You will see 299.36 will be equals to mass flow rate of fuel plus mass flow rate of oxidizer. This implies 299.36 will be equals to mass. We will take this MF common plus oxidizer, and this ratio we know it is given in the question. This is 5. So 5 plus 1 6. So from here you will get the value of MF, that will be equals to 49.89, and it is close to our option D. Fine. Now the second question is, here in this question we have to neglect the drag effect, the gravity effect also we have to neglect. Then the initial velocity is given, that is V1 is given as 2.5 km per second. Okay. The velocity of the rocket at the burnout. How to determine the velocity of the rocket at the burnout? You see, when you start burning that stage, you had one velocity V1. At the burnout, you will be having some velocity V2. Okay. So because of the burning of fuel, the propellant, there is some delta V added to the rocket. Fine. We have to determine that delta V, and this delta V if you will add to the initial velocity, you will get the final velocity. Okay. We know there is a standard formula for determining delta V, that is rocket equation we are calling it GISP ln of m1 by m2. This will be equals to 9.81 into ISP is what? Thrust per unit weight, 10 to the power 6. This is also 9.81 into mass flow rate of propellant. We have just find out this is 299.36 to ln of 100,000 divided by 10,000. Okay. If you will solve this, this delta V will comes out. This MP is equals to 299.36. You will get delta V as 7691.7 meter per second, which is close to 7.61 kilometer per second. So V2 will be equals to V1 plus velocity added due to burning. V1 is given in the problem 2.5 plus 7.69. This will be equals to 10.2 kilometer per second. I'm sorry, kilometer per second. Okay. So this is our answer. This is option C. The next question is, in a multi-stage axial flow compressor which is operating at an adiabatic efficiency of 0.9, the total pressure is given, that is 11. The ratio, the total temperature at the inlet of the compressor, the inlet temperature is given as 335 Kelvin. The stagnation enthalpy rise across each stage. So, enthalpy rise across each stage is 37 kilojoule per kg. Okay. Value of gamma is 1.4. Cp is 1.005 kilojoule per kg Kelvin. Now, the total temperature raise across the compressor is. How to determine? Let's draw the GS diagram first. You see, this is our delivery pressure. This is our initial pressure P1. This is delivery pressure. If the compression is the isentropic, then it will look like this. But the actual process doesn't happen like this. The actual process is like this. This is the state 1. This is the state 2. This is the state 2 dash. Okay, if the compression is isentropic. Now, the efficiency of the process is given. So, efficiency will be equals to divided by T2 minus T1. We know this value of neta, that is equals to 0.9. This will T1 you can take common, T2 dash divided by T1 minus 1 divided by T2 minus T1. Okay, this is the temperature rise, actual temperature rise across compressor. Now, this T2 minus T1 will be equals to T1 into this T2 dash by T1 will be written as Rp to the power gamma minus 1 by gamma minus 1 divided by this neta 0.9. Okay. Now, if you solve this, this will T2 minus T1, you will get 366.26 Kelvin, or it is similar to 366.3 Kelvin. This will be our answer. Now the next question is total number of stages. You see, this is the temperature rise across full compression process. Okay. Now using this is delta T total. Okay, across the compressor. So delta H total will be equals to what? Total enthalpy raise will be equals to Cp into delta T total. Fine. Cp is given at 1005 and we have got delta T total as 366.26. Okay. 26. Now the number of stages will be what? Total enthalpy rise due to compression to the enthalpy rise per stage. Okay, so this will be equals to 1005 to 336.26 divided by delta H. This value is given as 37 kilojoule per kg. Now you will compute this, you will get very close value 10. 9 point something you will get, this is close to 10. So your answer is B. Okay. Now, okay, this much question from Propulsion was asked in 2008 Aerospace paper. So for the regular update you can subscribe my channel, and if you are having any suggestion for us, you can comment in our comment box. Okay, thank you.